Greetings, AP Chemistry students. I apologize for promising a short lesson yesterday and not delivering, so today I'll try and do a little better. The first thing I want us to do is take a look at sulfate, SO4 with a -2 charge. Now, if I just asked you to draw a Lewis structure for it, I imagine that most of you would come up with this. On the other hand, I want us to also consider this alternative Lewis structure for sulfate and see if, when we evaluate it on the basis of formal charge, which one of these is better, the option on the left or the option on the right. So pause the video, take a minute, and see what you think. All right, so let's actually calculate what the formal charge is here. Oxygen normally has 6 valence electrons, but this oxygen right here has 1, 2, 3, 4, 5, 6 plus half of a pair. So that's 7. That's an extra. So its formal charge is -1. Let me write that a little better. This one has a formal charge of -1, -1, and -1. And then the sulfur in the middle normally has 6 valence electrons, but only has 4. So that makes it +2. Then let's compare this strange resonance structure over on the right side, where sulfur is violating the octet rule, which it can do because it is in period 3. So the oxygens on the top and the bottom are exactly the same as the ones in the previous structure. So they're at -1 and -1 and -1. But the oxygens on the left and right have a formal charge of 0. And the sulfur also has a formal charge of 0. And then down here it'd be -1, -1, 0, 0, and 0. So if the College Board just asked you to draw a Lewis structure for sulfate, this is the structure they would expect you to draw. But if they asked you to consider this structure on the right, on the basis of formal charge, it is a better option. Now, I want us to look at a few other things that we need to note. First of all, hydrogen and fluorine will only form one sigma bond, right? That's all they can do. Then we have oxygen forms two sigma bonds, and nitrogen can form three sigma bonds, and carbon forms four sigma bonds. Now, these are the max they can do. They can form one, like oxygen can form one sigma bond or two sigma bonds, but it cannot bond with three different things. Nitrogen can bond with three different things as a sigma bond, but it will not bond with four different atoms. And carbon can bond with four, but obviously, since it can't violate the octet rule, it can't go beyond that. Which leads us into a couple of things. There was a molecule that it asked you to consider last night, the HNO3 molecule. So the least electronegative atom is going to go in the middle, which is going to be nitrogen. And then it may require a little bit of knowledge you may not have had, but since nitrogen's in the middle, we can't just connect all three oxygens plus the hydrogen to the middle. Also, you may be aware that nitrate as a polyatomic ion exists. And so you take nitrate and you take H plus and you put them together. So let's first just draw nitrate. It's going to have three oxygens around it with a -1 charge. So it's got 6, 12, 18, 24 electrons or 12 pairs. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It would need to have a resonance structure with a double bond. So let's go in and just draw one of these cases here. And then if we add an H plus to this, we're not changing our electron count, but that hydrogen is going to attach itself to one of these oxygens. It can't go into the nitrogen because nitrogen can only make 3 sigma bonds. So it's going to have to attach to one of these oxygens. And it is really not going to attach to this one on the left over here because oxygen, first of all, really only wants to make 2 bonds, not even just sigma bonds. It really only wants 2 bonds, period, if it can help it. So let's attach it to this oxygen down here. Well, now what we would be doing is setting up a resonance structure between this oxygen and this oxygen. So the resonance structure would be and I'm going to draw that as at an angle, and I'll explain why in just a moment. And it's really probably best to draw this one over here at an angle as well. And the reason I do that is because the arrangement around this oxygen, because now we're going into some larger molecules, the arrangement of the electrons around this oxygen is going to be in a tetrahedral framework. So the shape around here would be bent. In other words, this bond angle is going to be less than 109.5 degrees. And then if you were asked, well, what's this bond angle? Well, this nitrogen has 3 things attached to it, so it's going to be on a trigonal planar framework. So this angle is going to be 120 degrees. So this is analyzing some more complex structures than we've done previously, right?